Hi everyone. In this video I will explain section 4.1 from Math111 طلاب السنة التحضيرية قسم العلوم بجامعة الإمام عبد الرحمن بن فيصل بالدمام. Okay, so first of all we want to determine whether a relation is a function. In order to know that we have to know first what is a relation and what is a function. Okay, so imagine a machine, and every machine, as you know, we put an input in that machine and then we get the output. So the relation is working just like this machine. We put something in that machine to get another thing. Okay, so a relation is a set of ordered pairs. Now, what is the ordered pairs? What is the definition of ordered pairs? The ordered pair, just like this, A and B, يعني الزوج المرتب A and B. So as you see in this one, we have two letters, A and B. A is called the X values or the X component, and B is called the Y values or Y component. And this one is called the order pair, يعني الزوج المرتب. وهذا إحداثي X وهذا إحداثي Y, يعني X component or Y component. Now we use an example here we have, they give us a set مجموعة 1 and 2 and another set B 5 and 6. Okay, and they ask us to find out 4 different order pairs by using A as an X component and B as the Y component. So for the first one, I will just set this 4 different order pairs. Since here I can take 1 in the X component and 2 also as X component, then I will use B to write the Y component of the order pairs. So I'm going to write here 5 and here 5, and then I will write 6 with 1 and 6 with 2. So here we have 4 different order pairs by using set A as X component and set B as Y component. Okay, so as we said, relation is a set of order pairs. This is the relation. So every person has a blood type. As you see here, we have Nawaf, Fahad, Ahmed, Ziyad, Ayman. We set those people to the blood type of each one. So for Nawaf, the blood type of Nawaf is A, so we write Nawaf then comma A. The blood type of Fahad is A also, so we write that as an order pair, Fahad then comma A and between parentheses. Also for Ahmed, the blood type of him is AB, so we write this relation as an order pair, so Ahmed then comma AB. Also here Ziyad then comma O and Ayman comma O between parentheses. So this is this set, if we put those in a set like this, يعني قواس مجموعة set, and then we put each order pairs, then we put a comma in between. This set is a relation. This set is the relation. So also another relation, for example, every cell phone in Saudi Arabia has a 10-digit phone numbers. This is another relation. Okay, now to determine whether a relation is a function, we have to what is the domain and the range of the relation. So the relation, as we said, is the order pairs, and the domain of that relation is the first component of the order pairs, while the range is the second component of the order pairs. Now let's take this relation that we already talked about, and I want to find what is the domain. So since the domain is the first component, so the domain is the name here, which is Nawab, Fahad, Ahmed, Ziad, and Ayman, while the range is the second component, which is A, B, and O. Okay? So again, the domain is the first the set of this component, while the range is the set of all second component. We can write the domain as this, and we can also write the range as this. Okay, now a definition of the function is a relation. So the function, any function, is actually a relation, but with a condition. The condition here of the function is that each element in the domain corresponds to exactly one element in the range. يعني كل عنصر بالدومين يرتبط بعنصر واحد فقط في الرينج. As you can see here, each element in the domain correspond to exactly one element in the range. كل عنصر بالنسبة للرسم السهمي هذا، اوكي، كل عنصر من الدومين يطلع منه سهم واحد فقط، اوكي. مو مشكلة if the one element in the range get two row, that's fine, but each element in the domain just يعني one row come out from it, only exactly one row. So this is explaining what does it mean by each element in the domain corresponds to exactly one element with the range or in the range. So also here in this relation, okay, this relation, we can see that this is not a function because this element has two rows, and this is not correct. It should only have one row, okay? So that's why this relation is not a function. So all functions are relation, but not all relation are function. Okay, يعني العكس مش صحيح. Okay, here we have an example. Decide whether each relation defined a function. So we have here A, B, and C. Those all are relations, but let's see whether they are functions or not. So for the first one, we can see that each element in the domain correspond to exactly one element in the range. Okay, so we don't have, if you are looking at the relation that is written in this form, you have to notice the first component, whether it's repeated or not. So since the first component is not repeated, so that means this is a function. But here for G, we can see that the first element is repeated one time with 2, and the other time is 1 correspond to 3. So it's look like 1 got 2 row, which is wrong. So this is not a function. For H is a function because as you can see, the elements in the X component are not repeated. They are totally different. So yes, this is a function. Okay. So let's try these relations. We have this relation, and we want to decide whether this relation is a function or not. So as I said, we just noticed the first component. We can see that the first component for all the order pairs are different. It's 1, 2, 3, 4, 5. So yes, it is function. Because you can say because each element in the domain corresponds to exactly one element in the range. Okay, so we can represent the function in more than one way. We can represent a function in like this, or like this one, or like this one. So this is the table, this is the mapping, and this is the graph. So we can represent a function in any form of these, or any relation actually, we can correspond it in this way. Now, if you have this form of the function and you want to just study the relation, whether it is function or not, for the mapping, you just notice that each element in the domain has only one row, okay? It has only one row, so yes, it is a function. Now for the table also, we can see that those elements are totally different. Now we can't have another one here that correspond with different, for example, with 5 or something like that. So if it's something like that, it would be not a function. But since all the elements in the domain are different, so it is a function. Also here, we don't have two dots above each other's. If we do have two dots above each other's, it wouldn't be a function, but since the whole functions are, or all the points are different, it would be a function. So 1 has only one number in the range that correspond with it. Okay, so let's see this exercise. We have the mapping here, and as you can see, all the elements has only one row, so yes, it is a function. Here also 1, 2, 3, they are totally different, so yes. And for this one, there is two dots above each other's, which means that 1 correspond with 1 and also 1 correspond with 2, which is not accepted in the function. So this is not a function. Okay. Now we also can define a function by drawing the line or drawing the relation. So we have here this relation y equal x plus 1. I want to define whether this is function or not. So what we did over here, that we draw this line y equal x plus 1, and it is something like that. And we can see that the graph is a line, and for that we can see that each element in the domain correspond with exactly one element in the range, one element in the range. So yes, this is a function. Also, some of the functions are defined by equations, and it could be, for example, quadratic equations or absolute values equations or cubic equations. So it is important to recognize that not all the equations are functions. So here, yes, it is a function because, as you can see, it is linear equations, and for the linear equations we will have a line, and obviously you can notice that each element in the domain correspond with exactly one element in the range. But for this one, sometimes is not a function. The equation will not be a function. An example of the equation that represent a function here we have, and this is the example of equations that represent no functions. You can just identify that easily also by drawing each one of those. Let's see, for example, y equal x squared. Okay, and if we draw this one, it would be something like this. This is y equal x square. We can see that each element in the x correspond with exactly one element in y. Here another different element of x, for example here x1, x2 correspond with the same value of y, and that's totally fine because for example if this is 1 and this is 1 and this is negative 1. So 1 correspond to 1 and negative 1 correspond with 1 also, and this is fine in the function. The necessary things that 1 does not correspond to two values, and that's is not in this graph. Okay. Also, if we want to draw the y equal the absolute values of x, it is something like this. Okay, so same things, we can see that each element in the domain correspond with exactly one element in the range. And for y equal x to the power 3, okay, it is something like this, and this also the same thing. Okay. For this one, we can see that it's like a slightly different between the first one and the second one. This is x equal y square, and if we draw this one, it would look like this one, like this. And we can see that one values of x correspond to two values of y, so it's not a function. Also for this one, this is a circle. Okay, and for the circle we can see that we have one values of x that correspond, for example here this value of x correspond to two values of y. X equal the absolute values of y, it is something like this, and we can see one values of x correspond to two values of y, and this is also not accepted in the function. Okay, so here we have also another functions that defined by equations. This is a relation y equal x square, and when we solve the relation for y, we can see that y equal plus and minus x. So here we have another way to define whether a function is whether a relation is not a function. We can solve for y. So also for this one, when we solve it for y, we can see that y get two values, and for this also y equal two values of x. So which means the equation represent no function because each values of y, or here we means by yx, has two values of y. Also here x has two values of y, and also in this case x has two values. Anyway, so this is such a point that is on the graph. We have these 2 points on the graph. As you can see, there is 1 point of x, okay, corresponds to two different values of y. Here also one values of x correspond with two different values in y. Here one x correspond to two different values of y. Anyway, so here we gotta have this exercise to determine whether a relation is a function. We have two relation over here. The first one, y equal root x. If we draw this one, we would have something like, okay, something like this. And as you can see in this one, we can see that each values of x correspond with exactly one values of y, and so on. Now, how can we find out by using another method? So this, we already said that this is a function. When we draw, we can also solve for y. We can see that y square equal x Okay, so by squaring both sides, and also here for b, we have y equal plus and minus root x. So as you can see, we have that each values of x correspond with two values of y, and this we already talked about it over here when we draw it. Okay, this is the drawing of it. And also here, y squared equal x, we can solve it, solve the relation for y and find out that x correspond with two values of x, of y. So this is not a function. Okay. Now we have another test, the test to find out whether a relation is a function by using the vertical line test. So what's the vertical line test has to do with the equations. If we draw a vertical line, as you can see over here, a vertical line on the graph, we can see that that vertical line intersect the graph in only exactly one point. In this case, we can say that this one is a function. Now let's try that over here in the second drawing. We can see that the vertical line intersects the graph in 2 points. So in this case, this function is not, this relation or this equation or this graph is not a function, not a function. Okay, this is the graph for x equal y squared, and this graph for y equal x squared. So by squaring y, it means that we get two values for one value of x, but it's okay to square x because that means we have two values of x for the same values of y. x1, x2 for y is fine, but x get two values of y, this is not fine. Okay, so here we gotta use the vertical line to figure out whether the graph is representing a function or not. So for the first one, when we draw the vertical line, we can see that it constructs the graph in only exactly one point, so this is a function. But for B, the graph construct, the vertical line intersect the graph in 2 points, which is not accepted. This functions is y equal root x. We can see that the vertical line intersect the graph in exactly 1 point, so it is a function. Okay, another drawing here, we will gotta decide whether the relation is a function by using the vertical line. So when we draw a vertical line in this one, we can see that the vertical line intersect the graph in 2 points, so it is not a function. But for B, wherever I draw the vertical line, we can see that the vertical line intersect the graph in exactly 1 point each time. Okay, so yes, it is a function. Okay, so in this we have a function defined by an equation. And as we said before, we can define the function by equation or by mapping or by, for example, the graphing or by writing it in a set. So when we write the function in an equation, like for example, f of x equal to x plus 5, we need to know that f is the name of the function, and the rule of the function, it takes each values x to in the domain to f of x in the range. Okay, so for example, for this function, we can see that this function take each values x and times the x with 2, then add 5. So we get f of x. For example, if we want to find out f of 0, so we have to times 0 with 2, then add 5. So this would be 0 plus 5, which equal 5. So the image of 0 is 5. The same things with f of 1. So we will take 1 and times it with 2, then add 5, and then we will get 7. F of 2, so f will take the 2 and times it with 2, then add 5, so we will get 9. Now we can graph or write that, draw that in the mapping form. So we have this is the domain or the value of x component, which is 0, 1, and 2. And in the range, we have the values of f of x, which is 5, 7, and 9. So we can write those numbers over here. Okay. Example, function notation. Write each function's y f of x. So we have here 1, 2, 2 and 5, 3 and negative 1. So 1 and 2 means that the image of 1 is 2. And 2 and 5 means the image of 2 or f of 2 equal 5. 3 and negative 1 means that f of 3 equal negative 1. Okay, for b, y equal x plus 1, we can just replace y and write f of x. So we means by y is that f of x equal x plus 1. In the mapping here, we have 1 and 2, so which means f of 1 equal 2 and f of 2 equal 3 and last f of 3 equal 4. Okay, also we have over here in the graph the image of 1 is 2, so f of 1 equal 2, and then the image of 2 is 2 or 3, so f of 2 equal 3, and last the image of 3 is 4, so f of 3 equal 4. Okay, so this is what we call the function notation. Now, if a function y equal f of x is given explicitly in terms of x, then the corresponding y component of x, which is, for example, a, is f of a. So we don't have to write the y component as y, we can write it as f of a, and it's found by substituting x with a. So for example, here we have f of x equal x squared minus 1, and the question asks us to find out f of 1. What is f of 1? So f of 1 is f of 1 is 1 square minus 1, which equal 1 minus 1 equals 0. And f of 2 is 2 square minus 1, which equal 3. Okay, now f of 3a, so we're going to replace x with 3a, so 3a all square minus 1. Now the square will destroy, we will destroy the, for f of 3a, so we're going to replace x with 3a, and then we will square everything, 3 and a. So the 3 square is 9 and a square is a square, then minus 1. Same things with f of a plus 1. So this would be the value of x. We will replace x with a plus 1 minus 1. Then we will distribute the square. So a square plus 1 square plus 2 times a times 1, which is 2a. and this -1 is here. So we will just simplify more to get a squared plus 2a. Okay. For example, if we want to find f of -1, so in the main equation, we will replace x with -1. So we would have -1 squared minus 1. Now we know that -1 squared is 1. So 1 minus 1 equal 0. Okay. Evaluate the function. The graph of the function over here is given on the right side. They give us the graph of the function, and we want to find out f of 0. Find f of 0 and find f of 1, f of 2. So to find out f of 0, we will not move through the x-axis. We will stay on the origin. So then we will go up until we hit the graph. So we're going up until we hit the graph. We're gonna hit the graph over here. So the point is 5. So f of 0 is 5, or we can write the coordinate, which is 0 and 5. Okay, f of 1, so we will go to the 1, which is here. This is 1, this is 2, this is a 3, and this is 4, and this is 5. Okay, so the same things, we will go up until we hit the graph, then we will go horizontally to the y-axis. So this is the point, which is 2. So here is 1, 2, 3, 4, and 5. Okay, what about f of 2? So we will go to the 2 in the x-axis, then we will go up until we hit the graph, then we will go horizontally to see the point, which is 1. So it is 1. Now 4 times f over 3, so first we gotta find f over 3. So we'll go to the 3 point on the x-axis, then we will go up until we hit the graph, then we will go horizontally until we hit the y-axis, so the point is 2. So we're gonna times this 2 with the 4 over here. 4 times 2 equal 8. Okay, so this A, B, C, and D. It gives us the value of x and ask us to find out f of that value. Now, what about if we don't know the value of x, but we already know that the value of f of x, which is 10. So this is gotta be in the y-axis, okay, or the value of y. So in this case, I will go to the y and to the point 10 on the y-axis, and then I will go horizontally until I hit the graph. Then I will go vertically to the x-axis. So the point is 5. Okay, same things here. F of x equal 2. So I'm going to the 2 in the y-axis, then horizontally until I hit the graph. Then I'm going down to the x-axis. So the value is x equal 1. And also I have another value over here. So when y equal 2 or f of x equal 2, the graph, this point has a 2 image on x. So I'm going to hit the graph in 2 points. As you can see here, I'm going to hit the graph in this point and this point. So I'm going down to see the value of x. So the value of x is 1 and 3. 1 and 3. So again, the domain is all x component and the range is all y component. So for this example, we want to state the domain and state the range for each one of the relations. For the first one, the x values is the domain. So -1, 0, and 1 are the domain. And 2, 3, 5 is the range. For B, this is the domain 1, 2, 3, and the range is 7 and 8. For C, it's a little bit different in C and D in the graphing, so we gotta see how we find out the domain and the range. For this one, if I have a row over here, an open row, so it means this goes to the negative infinity. And the negative infinity up to, as you can see, it's going like this. so to the plus infinity. So the domain is from negative infinity to plus infinity. We can also know that by just imagining that you are putting your pencil above the x-axis, and you will see that while you're putting your pencils in your x-axis, okay, like this, okay, you can see that you are constructing the graph all the way long. okay، يعني تمشي البنسل حقك على الاكس اكسس وراح تشوفي انك تقطعي الجراف على طول ما انت ماشية من اليسار الى اليمين. The same things, so since here we have a row, it means from negative infinity. That means I'm going through the graph all the way, and also here. Okay, there's a slight difference over here. If the graph, if this one is exactly vertical, like this, that means I'm going to stop at this point in x, but since this is a little bit, okay, in between, so it means it goes to the negative infinity from the x as well. Okay, now for y values, or the y component, we can see that we are starting from here. As you see, this is a horizontal, it's not a vertical. That means I'm gonna start from this point, which is 1. Then I will keep going up until infinity. So for the range for this one, it is from 1 included to infinity. This is the range. Okay, here the difference between this one and this one, that means we are stopping over here at this point, but for this one it's continuous to the infinity. So for D, I can say that the domain is starting from this point and ending at this point, so from -1 to 1. And for the range, we are also starting from this point and ending at that point, so from -1, from 0, here is the value of y, so from 0 to 3 included. Okay, so for the last one, f, what is the domain? It is easy when it's written like this. So the domain is all those points, and we don't have to repeat the numbers if they are repeated. And the range is all those points. Okay. Okay, let's try this example. What is the domain and what is the range? So if we are just putting the pencils, we will see that the pencils is touching the graph from negative infinity, and we are keeping touching the graph to the plus infinity. So this is the domain. And the range, we will start from this point, which is -2 included, and then we go all the way up to the infinity. So this is the range. For this one, it is continuous in the x-axis and also in the y-axis, so R for the domain and also R for the range. Okay. Okay, example 8, decide whether each relation with given graph defined a function and state the domain and the range. For the first one, 3x plus 1. Okay, when we draw this as a line, and I said before, if it's a line, it means it is a function. So yes, it is a function. When we draw it, we can notice that each element in x correspond with exactly one element in y. And also for the line, the domain is R and the range is R as well. So as you can see, it is continuous from both sides, okay? From here and here, so, and it is in between, يعني مش directly vertical ولا horizontal، مايل بين وبين. معناتها ياخذ القيم الإكس لما لا نهاية وأيضا قيم الواي لما لا نهاية. Okay, y equals square root of x plus 1. This is the drawing of the graph, and it's obviously a function because each point in x corresponds with exactly one point in y. And also, if we want to find out what is the domain, we can see that the domain, which is x values, is starting at this point, which is 1, and it's continuous to the infinity. So from negative 1 to infinity, while the range is starting at this point, which is y component, and also start continuous to the infinity, so 0 to infinity. Okay, the equation x equal y square, and when we draw it, it would be something like this. And we can see that 1 point of x corresponds to 2 points of y, so it is not a function. Okay, let's see what is the domain. The domain, which is the x values. So x values starting at this point, which is 0, and ending to the infinity. While y values, so we can see we always gotta have a point in y from the bottom and also from the top. So it would be from negative infinity to plus infinity. For this graph, we can see that we have, when we draw the vertical line, we can see that the vertical line intersect the graph in exactly 1 point, so it is a function. The relation is a function. Now, for the for the domain and the range, we can see that all the numbers in the x-axis are included in the graph, except that the graph does not touch the point of x when x equals 0 or y equals 0. So it would be exactly r minus 0, or we can write it as negative infinity to 0, union 0 to infinity, as well the range. So the same things for the domain is also for the range. Okay, a function notation, we can write the functions notation as this one. And this means that y is the output and x is the input and f is the name of the function. Okay, so for a function f, x represent the first component and y represent the second component. Then we use the notation y equal f of x, where x and y is the ordered pairs that we talked already. If we want to find out the domain of a function, so we have to look at the function carefully. If the function is a polynomial, and we know previously how to find out whether is a function is polynomial, remember that the exponent of x has to be an integer, positive integers, or non-negative integers. Okay, so as you can see, this is a form of polynomial since the power of x is 3 and 2. Okay, so if the function polynomial, in this case, the domain will be R. Okay, the domain will be R. So we don't have any problem. We don't have any values that makes this function undefined. Okay, so the excluded x values, the x value that we want to exclude it, يعني نستبعدها، ما في أي قيم, none. There is no values of x that has to be excluded. Okay, so this is in case that my function is a polynomial. Now, what about if my function is a rational, يعني بسط ومقام? In this case, I have a problem. I have to exclude x value that makes the denominator equal 0. يعني راح استبعد القيم اللي تخلي المقام صفر. So for example, in this one, we can just solve the denominator for 0, like x squared minus 9 equals 0. And in this case, x squared equal 9, so x equal plus and minus 3. So these two values of x makes the denominator equal 0. Okay, so I'm going to exclude those values. We can say, for example, x does not equal plus 3 and minus 3, or we can just write the domain in an interval just like this. So from negative infinity to negative 3 open, then open again from negative 3 to 3, then from 3 to infinity. So it looks like I have here negative 3 and 3, and I will just have all these intervals, but this interval and this interval and this interval, but without including negative 3 and 3, because these two values make the denominator equal 0. Okay, now for the radical, if the function is radical, which means I have root, or the x values is under the root. So in this case, as you know, the negative values under the root is not accepted on the real numbers. So I'm going to exclude those values that result in a square root of a negative number. So in this case, I will just take whatever under the root, so x minus 5, and I want these values to be more than or equal 0. So I'm gonna just move this to the other side, so x would be more than or equal 5, and only this value, these values, which is from 5 to infinity, including 5, makes the function define. Otherwise, like when x less than 5, this makes this interval makes the denominator undefined. Okay, so here we have an example of how to find a function. Okay, so let's solve this one. For the first one, I have a rational function. So in this case, I just doesn't want x minus 3 and x minus 4 to equal 0. So I don't want these values to equal 0. So I'm just going to solve this just like solving quadratic equation or linear equation or anything. So for this one, this is a quadratic equation. So two values equal 0. So either the first one, so you know that we used to solve this like this, so it's fine. So either the first one equals 0, so in this case x equal 3, or x minus 4 equal 0, so x equal 4. So these two values, this value and this value, makes the denominator equal 0. So as you see, these two values makes the denominator equal 0. So I don't want those two values. So that's why the domain is r minus 3 and 4. So I'm just going to exclude these two values from r. Yani everything is fine except these two values. Okay, for B, part B, since the radical in the denominator is in the denominator, so I just doesn't want the value under the root, okay, this value that is under the root, okay, I just doesn't want this value to be 0 because it's located in the denominator, and also I don't want this value to be negative. So the only values that makes the the function define is that the value under the root should be more than 0. Okay, so we used to say here it's more than or equal 0. Okay, we used to say that it is more than or equal 0, but because this does not located in the denominator, but if it's located in the denominator, I will just write more than 0. So now I solve this. As you remember, we solved this by finding the zeros. I have two zeros here when x equal 3 and when x equal 4. So in the number line, I have 3 and 4. Then I will test the sign through the intervals that I have. So by picking values, for example, I'm going to pick here, let's say 3.5, a number between the 3 and 4. And here I can pick 5, or let's say 5, and here I can pick -5. Okay, so when x equal -5, this value, okay, this would be -5, -3, and here -5, -4. Now let's check the sign over here. This would be negative, and this would be also negative. So negative times negative would be less than 0. So when x equal -5, I will have a negative sign. Now let's try x equal 5. So when x equal 5, I would have 5 minus 3 times 5 minus 4. So this value would be positive, and this value would be positive. So positive times positive is positive, okay? And in this case, this would be positive, okay? Sorry, in this one, negative times negative is positive. Okay, so also here positive. Okay, the last point is when x equal 3.5. So I would have 3.5 times, minus 3, then 3.5 minus 4. So this would be a positive, but this would be negative, and positive times negative is less than 0. So the answer would be negative. Okay, now let's compare this one. Since in the question we want it to be more than 0, we want it to be positive sign, okay? Here we have to have a positive. So I will choose this interval and this interval in my domain. So the domain should be from -infinity to 3, and I will not include the 3 because, as we said, the 3 makes the denominator 0, and this is not accepted. Union from 4 open to infinity open. Okay. So same things here. We have determine the domain of each of the following function. The first function is 1 over x squared minus 2x minus 3. The second function is g of x equal 1 over the square root of x squared minus 1. So let's see how we do this one. Okay, so for the first one, since we have a rational function, we have to find out the values that makes the denominator equal 0. So x squared minus 2x minus 3 equals 0. Then we will solve this quadratic equation. So x squared okay, if we have the figure over here, it is a graph of a function, and we want to find out the intervals in which the function is decreasing, increasing, and constant. So let's see where the function is decreasing. As we said, we have to start from the left to the right. Okay, so it looks like we are drawing the function. So here the function from the left to the right is going down, and also in this part the function is going down, and also in this part the function is going down. Okay, so the interval in this case would be from, since this is open, so it would be from negative infinity to negative 2, okay, which is the first one. Then for this one is from 0 to 2, which is this one. Then for the third one, it's from 6, this point, 6 to infinity. So from 6 to infinity. Okay. Now let's check where the function is increasing. So the function is increasing when it's going from the left to the right, it's going up. So here it's going up, and also here it's going up. So the first one would be from negative 2, this one, negative 2 to negative 1. Okay. And for the second interval, which is this one, so it's from 2 to 6, from 2 to 6. Okay, the only interval that makes this in this constant is from negative 1 to 0, which is this one, from negative 1 to 0. Okay, so as you can see, the intervals are classified according to the x-coordinate. So when we want to write down the intervals, we are looking at the x-exponent or the x-coordinate. Okay, so also here we have another example. We want to find out where the function decreasing. Okay, so decreasing, it means going down. So in this part it's going down, this part is going down, which is from negative 5 to negative 2. We can see that this is a close over here. It's not a row. If it's a row, we get a right negative infinity, but this is not a row. Okay, so from negative 5 to negative 2, the other one is from 0 to 2. Now it is increasing. It is increasing in this one only. So it's from the left to the right, it's going up. So from 2 to infinity, from 2 to infinity, because we have here a row, it's open, so it means infinity. And the only part that the constant, the graph is constant, is in this part, this one, from negative 2 to 0, from negative 2 to 0. Okay, now what is the domain of the function and the range of the function? To find out the domain of the function, you just can notice the where the graph, let me see. So this is the x-axis. Now the graph is starting at this point, as you can see, because here is closed. So it's starting at this point, and since here it's open, so it does not end in any values of the x, of the right side of the x-axis. So it would be to the infinity. So it would be from negative 5 to infinity. Okay. Now let's check the range, and we said already that the range is the y component, or the we can look at the y-axis. So we can see here, this is continuous, so it can take all the values in the y, but from the bottom we don't have any values, and we don't have any graph here, so it starts exactly at this point, where this point, the value over here is 0 for y. So it's from 0 to infinity. Okay, so since here there is no graph, so we gotta start at this point, which is 0, then the graph is continuous to the infinity, so that's why the values of y would be infinity. So it's from 0 to infinity. Okay. In this example, we want also to find out the increasing, decreasing, and constant of the function. The interval over here, this one is increasing, and also this part is increasing. Okay, this is going down, so this is decreasing. And the last thing is constant, which is this one is constant. So if we want to write the intervals, since here we have a row, so it would be from negative infinity to this point, which is negative 1. So from negative infinity to negative 1. And the other increasing is from 0 to 1. From 0 to 1. Okay. So the decreasing part is from negative 1. It's from negative 1 to 0. From negative 1 to 0. And the constant is from 1 to infinity, because here is open, so from 1 to infinity. Okay, let's check this exercise. So this is going, here is going down, and also this is the only thing that going down. Okay, so this would be decreasing, and this is constant. This part is constant, and then the rest, as you see over here, the rest would be, sorry, and the rest would be going up. Okay, so this all is increasing. So the decreasing would be from negative infinity to negative 2. Okay, then we have the constant, so this is the decreasing. Then the constant would be from negative 2 to negative 1. Then we have the increasing, which is from negative 1 to infinity. Okay, now what is the even function and the odd function? The even function, like this function, like this one, this is an even function. So why we call this one even function and this one is odd function? Okay, so we call the even function is even function when f of negative x equal f of x, which means, as you can see here, the image of x equal the image of negative x. This is the image of x and also the image of f of negative x. Okay, while also we can see that this function is symmetric through the y-axis. Okay, متناظرة حول محور y. While the odd function, we can see that the image of x, which is f of x, equal to the and the image of negative f of x. Okay, here is f of negative x is equal to the image of negative f of x. Okay, because let me tell you this in, for example, if this is 2, this would be 8. And if this is negative 2, this is would be negative 8. Which means f of 2 equal 8 and f of negative 2 equal negative 8. So f of negative 2 equal negative f of 2, which is negative, and this one is 8. Okay, so also we can see that the graph is symmetric through the origin. So if the graph is symmetric through the origin, the function would be odd, and if the graph is symmetric through y-axis, the function would be even. So as you can see here, we have an odd function, okay, and this is odd because it's symmetric through the origin. Also, we can check by following this formula that f of negative x equal negative f of x. And this function is even function because f of negative x equal f of x. While this one is neither odd nor even, okay, because it's not symmetric through the origin or y-axis, and also it does not satisfy these two status. Okay, we have here such an a function, and we want to find out whether the function odd or even. Okay, so we can check that. Let me read this question, then we will solve those in details. So for the first one, x to the power 4 equal 1. So x to the power 4, we just have to find out what is the value of f of negative x. So I'm going to replace each x with negative x. So negative x to the power 4 plus 1. Negative x to the power 4 is x to the power 4, which is a plus 1, and this just like f of x. So I start with f of negative x, and I found that this equal f of x. And this is the rule of the even. So the rule of even says that f of x equal f of negative x. Okay? And the rule for odd says that f of negative x equal negative f of x. So since the rule of the even satisfied, we can say that f is even function. Also for b, I start with f of negative x. Then I replace each x with negative x. So negative x to the power 3 is negative x to the power 3. It doesn't change because the power is odd. And then I can take negative as a common factor. Then I left with x3 plus x, and this one is f of x, so negative f of x. So I start with f of negative x, and then I end with negative f of x, which is the rule of odd. So the function is odd. For part C, I start with f of negative x. I replace each x with negative x. Then I left with x squared minus x, and this does not equal f of x, does not equal negative f of x, so it's neither even nor odd. Now I have another rule you can follow in some in specific situations, not all the situations. So in case you have something like this, you can see the power of x. If the power of x, for example, this one, okay, you can write this one as x to the power 4 plus x to the power 0, because you know anything to the power 0 equal 1. So we can see that this has an even power, so the function is even. The function is even. Okay, for the second one, this one is x to the power 3 plus x to the power 1. And as you see, this is odd and this is odd, so the whole thing is odd. But for this one, we have this is even, and here is 1, which is odd, so even and odd, so it's neither even nor odd. Okay, so we can apply this one in these examples as well, and also we can just find f of negative x. So f of negative x equal 2 times negative x to the power 3 plus negative x to the power 5. Now, since the powers are odd, so the negative will stay. So this would be negative 2x to the power 3 minus x to the power 5. Then since I have here negative and here negative, I can take negative as a common factor. So I'm going to left with negative 2x to the power 3 plus x to the power 5. Now this one is just this one, which is f of x. So this is negative f of x. So since I start with f of negative x and I end with negative f of x, so I have an odd function. And again, it is odd from the beginning because the power over here of x all are odd. So the function is odd. So if we want to follow this rule, we can see that here x to the power 6 and x to the power 4, both of them even. So we can say directly that the function is even as well. And also we can find out f of negative x by replacing each x with negative x. So this is negative x to the power 4, and since the powers that I have here are even, so the negative will be cancelled. So I'm gonna left with x to the power 6 minus x to the power 4, and this just like the original f of x. So I start with f of negative x and I found out that this equal f of x. So the function is even. For C, as you see, this is even, this is odd, but this is even. So this is neither odd nor, so it is neither even nor odd. And if we want to apply the rule, so I'm gonna find f of negative x, so negative x to the power 5 minus 1, which is negative x to the power 5 minus 1. This does not equal f of x and does not equal negative f of x. So that's why it is neither. Okay, so that's all for this part. Thank you for watching. For B, g of x equal 1 over the square root of x minus 3 times x minus 4. So here we have two things. The first thing is that the radical, and we said for the radical, the value under the radical should be more than or equal 0. But since the radical in the denominator, so we want the value under the root, which is x minus 3 times x minus 4, to be only more than 0. So we will not put the equal sign because the value here in the denominator, okay? So we will not put the equal here, only more than 0. Now we're going to solve this just like solving the quadratic inequalities. And when we solve the quadratic inequalities, we find the zeros of the quadratic. Here the zeros is x equal 3 and x equal 4. So in the number line, in the 3 and 4, we're going to check the intervals, the sign of the intervals. So we're going to pick a number in between those zeros or those roots. So I'm going to pick here 3.5, and here I will pick 5, and here I will pick negative 5. So when x equal negative 5, I would have negative 5 minus 3 times negative 5 minus 4. So negative 5 minus 3 is negative, times negative 5 minus 4 also negative. And you know negative times negative would be positive. Okay, so the result here would be more than 0. Okay, for x equal 5, so here this would be positive. For x equal 5, I will have 5 minus 3 times 5 minus 4. So 5 minus 3 will result, the result will be positive, and 5 minus 4 also the result will be positive, and positive times positive is also positive, which is more than 0. So also here is positive. And for x equal 3.5, so I would have 3.5 minus 3, then 3.5 minus 4. And you know that 3.5 minus 3 is positive, since the 3.5 is more than 3. And 3.5 minus 4 is negative, since 4 is more than 3.5. So positive times negative would be negative, which is less than 0. So here is negative. Now, which intervals we would pick? That we would pick this interval and this interval, because those give us the value of positive or more than 0. So the first interval would be from negative infinity to 3 open, union from 4 open to infinity. Okay, so at those intervals, the value of the function would be defined, because the value of the denominator would be defined. Okay, the root would give us only a positive values, not 0, not negative. Okay, now let's check the exercise over here. We have two function as well, and we want to find out whether the function, what is the domain of each of them. So the first one is 1 over x squared minus 2x minus 3, and the second one is g of x. Okay, g of x equal 1 over the square root of x squared minus 1. Okay, so let's solve the first one. Since we have quadratic equations in the denominator, so we want the denominator to be a non-zero value. So let's find the 0 of the denominator, then we will exclude them from R. So what's the value that makes the denominator equal 0? Let's factorize this one. Okay. So we want to find two factors that their product equals -3, and the sum would be -2. And you know, to have a product of negative, it means one of them is negative and the other is positive. And since the middle is negative, so the large number would be negative. Now the two values is 3, or the two factors is 3 and 1. -3 times 1 is -3, and -3 plus 1 is -2. So, okay, so the two zeros, or the two roots, would be x equal -1 and x equal 3. Okay, so at those values, at those two values, okay, the value of the denominator would be 0. So the domain will be R minus these two values. And I don't want these two values to be in my domain, because these two values makes the denominator equal 0. Okay. Okay, so this was for part A. Now let's see g of x. For g of x, we have the same things. We have a root in the denominator. So the value under the root, the domain is, I can write this directly here. So the domain is when the value under the root more than 0. Then we will solve this one to find out exactly what is the value of x. Okay, so x, so this is a quadratic inequalities. I will factorize x squared minus 1 to x minus 1 times x plus 1. Now the roots would be x equal 1 and x equal -1. Then on the number line, I have 1 and negative 1. And then I will pick 3 values of x. For example, here I can pick 0, here I can pick 2, and here I can pick negative 2. Then we will check the intervals, the sign of the intervals. Now, when x, for example, equals 0, we can see 0, negative 1, and then 0 plus 1. This would be negative, and this will be positive. So negative times positive is negative or less than 0. So this is conflict with the original. So I'm not going to pick this one. Okay, here is negative. So I'm not going to pick this one. So we're going to try the other values. So for example, when x equal negative 2, it would be negative 2 minus 1 times negative 2 plus 1. Here is negative times negative, which is positive. So the value over here is positive. Okay, also when x equal 2, I would have 2 minus 1 times 2 plus 1, and 2 minus 1 is positive, 2 plus 1 is positive, positive times positive is also positive or more than 0. So the value over here would be positive also. Okay, so for this, in this case, since here is more than 0, so I'm going to pick this interval and this interval. So the answer would be from negative infinity to negative 1 open, union from 1 to infinity open. This is the domain. Okay, now we have the increasing and decreasing and constant functions. We have 3 types of functions: increasing function, decreasing function, constant function. This is a type of increasing functions. Okay, increasing functions means when we go from the left to the right, we can see that the function is going up. But when we go from the left, so that's why it is increasing, and تزايدية. But when we go from the left to the right, we can see that the function is going down. Okay, here the function is going down. That's why this function is decreasing or تناقصية. While the constant function, يعني الفانكشن الثابتة, we can see it is like horizontal, okay, horizontal, and there is no change. It is just same values for all the values of x, we have the same values of y, so it is constant. So that's why we call this one a constant.